Thanks everybody for attending. If you attended last week's fuel handling webinar, you'll remember that it was billed as fuel system design for gensets and boilers, and I realized halfway in that it was just too much for one webinar. So we ended up breaking it up, and Megan and I got busy and did this fuel system design for oil-fired boilers webinar a little early. And we're going to post it to the YouTube page, which is probably where you're going to be seeing it now. So let's get started. These are the national codes that we have to follow where we're doing a fuel system for boilers. NFPA 30, NFPA 31, NFPA 85 if the individual burner heat input is more than 12.5 million BTUs per hour. And if it's smaller than that, then we're going to follow ASME CSD1. And the differences are slight. ASME CSD1 lets you cut a few corners for smaller burners. Now, there is a very common misconception with NFPA 31. I've had more than one good engineer tell me that they can't put more than 3 PSI to a boiler because of this paragraph here in NFPA 31 that says the pressure to fuel supply inlet to an oil-fired appliance may not exceed a gauge pressure of 3 PSI, unless the appliance is approved for a higher pressure. And that's where every boiler fits in. They're all approved for higher than 3 PSI. And I would disagree. I would argue that a boiler is not an appliance. The NFPA 31 was written for teeny tiny little oil-fired things, not boilers. And I put in the appropriate similar paragraphs from NFPA 85 that makes no regard to a specific pressure. It just says that the piping that you use and the valves shall be rated for the pressure intended. One more point to make along those lines, and this is kind of skipping ahead, but here's a schematic, and it might be a little hard to read. Here's a schematic of how we'll typically do a fuel supply to a boiler. We go out of the pump set there in the little yellow box. We'll do a fuel supply header that goes to the 3 boilers. We'll go through a back pressure regulating valve, and then we've got to go back up to the main tank. We've actually got to go back up and over the main tank. And the main tank is typically going to be at least 10-foot diameter. Well, hydrostatic pressure alone for number 2 oil is 2.4 feet per PSI. So 2.4 times 3 is 7.2, which means you can't push oil higher than 7.2 feet without exceeding that 3 PSI limit. Forget about a back pressure regulator, forget about pressure losses in that pipeline. You can't even get the oil back into the main tank at 3 PSI. So we will return to this later, but if you take one thing away from this presentation so far, it's ignore that paragraph in NFPA 31. It's not applicable to boilers. And the paragraph includes an out for boilers. So anyway, moving right along. There's 4 basic types of oil atomization. And I started out life as a combustion engineer where I learned this stuff. And it's been relatively recently that I started doing gensets, but I thought I would start with showing everybody the different types of oil atomization so that you have a better understanding of what's going on at the burner. So the first type is rotary cup, which really isn't allowed anymore for emissions reasons. The only place we see rotary cup burners is in New York City, where the infrastructure tends to be really old. And sadly, most of the rotary cup burners you see in New York City are preferred burners. And some of them are 70 years old and still running great. And they're getting replaced for emissions reasons, not because they don't run. So sadly, a lot of rotary cup burners are coming out. And if you fall into that boat, call us, because we're the easiest way to retrofit a rotary cup burner to steam or air atomization. The second most common is steam atomization. It's mostly used on water tube boilers, and steam atomization works great because not only do you get the atomization effect of the steam, but steam is also high temperature, so it helps to make smaller particles out of the number 2 oil. You do have to be careful with steam atomization that you atomize the number 2 oil and don't vaporize it. We want to be burning small droplets. We don't want to be burning number 2 oil vapors. If you are burning number 2 oil vapors, the burner will make a very distinctive motorboating sound. And we mostly see it on water tube boilers that run higher pressures and run higher quality or drier steam. I have done steam atomization on large fire tube boilers, and the trick to that is it's got to be a high pressure boiler, you know, operating at least 100 psi, and you have to do a good job with your steam traps and insulating the line so that you get good dry hot steam to the burner, because that's one of the big things between water tubes and fire tubes is the fire tubes seem to have wetter steam. And with saturated steam, if you take any energy out of that steam, it's going to condense a little bit of steam into water, and we want to atomize some steam, not water. Finally, air atomization is super common. It's almost 100% of fire tube boilers. It works great. The downside to air atomization is that it's a pretty high consumable load. It's a lot of high pressure air you have to supply. So that can become expensive, not only for the electricity, but the maintenance on an air compressor. And then finally, the last one is pressure or mechanical atomization, which has been around forever. I've seen it on utility boilers made in the 1950s. And it's getting more popular in the United States because we're seeing more European burners in the United States, and all the European burners seem to prefer pressure atomization. So now we'll do a little more detailed information on these different types of atomization. So here's a chart. This is the most important slide of this presentation. This tells you the required oil pressure and the required oil flow for the different types of atomization. So if you're going to screenshot anything from this presentation, this is the slide. So the burner manufacturers that do steam atomization are mostly the American burner manufacturers, and way more common with water tubes than fire tubes. Mainly for the reasons I said in the last slide. Also, water tube boilers tend to be larger than fire tube boilers. So to use air atomization on a large water tube boiler gets to be really impractical because of the amount of air that would need to be used and the horsepower of the air compressor. So typically the required oil pressure is going to be 100 psi for a fire tube with an American burner on it, and 150 psi for a water tube. The required oil flow is going to be equal to the boiler consumption at high fire. And I've got a couple of slides coming up soon that'll show you how to calculate that. It's funny, I work with mostly genset fuel oil people that are really, really good, but they don't have much experience with boilers. So I get a lot of calls from genset people asking me how to figure out the oil flow on boilers. And you're gonna learn how in a couple of slides. Air atomization is the same. Your required oil flow is going to be equal to high fire boiler consumption. And we usually see air atomization on fire tube boilers, and most are going to require 100 psi. There is low pressure air atomization. I believe Cleaver Brooks does it on some of their burners, and that typically is 15 to 30 psi. So the right answer to this is check with the burner manufacturer, but this chart will get you in the right ballpark. Finally, pressure atomization, almost universal with the European manufacturers. And the ones we're seeing these days are Weishaupt, Riello, Oilon. I throw in preferred, we're American, but we will do pressure atomization sometimes. And I just saw a set of drawings for a Johnston burner that wasn't doing pressure atomization. They were doing air atomization, but they included an onboard pump. And if the burner manufacturer includes an onboard pump, regardless of their atomization style, it's going to fall into this category. So your required oil pressure is going to be negative 13 inches water column, because that tends to be the most that these onboard burner pumps can lift. and they want to see no more than 10 psi in the supply line or the return line. And then the required oil flow is the pump flow rate, and it's going to be much higher than the boiler consumption at high fire. And that finding that information really is the struggle with pressure atomized burners. So okay, moving right along. A little bit of a deep dive on steam atomization. It produces very small droplet sizes. It's probably the best form of atomization for clean combustion if you can get dry hot steam. You can get up to 8-to-1 turn down with steam atomization. And turn down is just high fire heat input on the burner divided by low fire heat input on the burner. And the more turn down you can get out of your burner, the better, because that allows your boiler to respond better to load swings. If a boiler is producing more steam than the plant has load for over a relatively short period of time, 10 or 15 minutes or more, then the boiler is going to shut down on high steam pressure on its operating steam pressure switch. And it'll usually come back on when that switch makes again. But you've got to go through the purge cycle on the burner and you've got to light off again. So shutting down the boiler, letting it draft cold air, and then purging it and lighting it back off again are kind of hard on the burner and the boiler. So we would prefer not to do that if we can help it. And high turn down out of the burner allows you to match the burner heat input or the boiler output better to the load of the plant. And as I mentioned before, steam atomization is almost a standard for water tube boilers. You will often see air atomization used for cold start on water tube boilers. They'll tee in an air line off either a dedicated compressor or a house compressor, and that's designed just to get the boiler running in case there's no steam on the header for steam atomization. We used to tell people that you weren't going to get above about 25% firing rate on atomizing air, cold start atomizing air, but it really depends on the orifice sizing in the burner gun. I've seen people get 50, 70% on atomizing air. So, but the rule of thumb is 25%. In terms of atomization quality, air atomization is second to steam atomization. It requires a lot of compressed air, typically at 100 psi. 8-to-1 turn down is available on compressed air, just like it is steam atomization, and it's pretty much the standard for fire tube boilers. Air atomization is also easier to use and easier to automate. With steam atomization, what tends to happen when you shut off the burner is all the steam in the steam line to the individual burner usually condenses when the burner's off. So you start out with a steam line that's full of water. So the typical light off sequence is to open that steam line while the boiler is purging, and then there'll be a hand valve, usually right at the burner, where you can see into the viewport. And water tube boilers in the old days were lit off by hand. Nowadays, it's more often to light them off automatically. But in the old days, you would sit right in front of the burner, and when the burner goes to purge, you would open up the steam line, dump all that water into the boiler, and then continue to run steam through that line to get the line hot and to dry out the line and dry out your steam. And then usually I would close it off when I hear the oil valves open, because I want the oil to get through the gun as quickly as possible and not have to overcome the back pressure from the steam. And then when you see just a little bit of oil spray coming out of the oil tip, crack open your steam line. That'll get you a good ignition, a good bright flame, and then open your oil and your steam globe valves all the way, and then the boiler's ready to sit there in low fire and warm up. And you should typically warm up a water tube boiler until it starts making steam at low fire before you let it get off low fire. Air atomization is much easier. You don't have to worry about wet steam. So with air atomization, it's usually automated so that the air line opens the same time as the oil line, and you get a nice clean light off every time. So this is what the guts of a air or steam atomizer looks like. There's two basic types. There's inside mix and there's wide jet. I'm showing you YJet because I was able to find a couple of good drawings of how this goes. And the left-hand drawing shows it, well, they both do. Oil comes out through the top, and then air kind of goes northeast in this drawing. And as the air goes past the oil, it sort of shears off that stream of oil and shears it into tiny little droplets. And then on the right-hand side, you can see that the oil and air mix goes through a larger hole that's drilled into the spray tip. And there's a little bit of science and a whole bunch of artistry into the design of these oil tips. Both the angle and the number of holes will impact how wide or how narrow your flame is and how it fits different furnaces. And part of a typical oil startup was you would go with the best oil tip or the tip that worked the best the last time you did this particular boiler, but sometimes you might have to get a tip that's 5 degrees wider, 5 degrees narrower, or has 7 holes instead of 9 holes, or something like that. So combustion engineers back in the day got to be pretty good at looking at an oil flame, and if it wasn't meeting expectations, tweak the oil tip and drill a new oil tip to clean up the flame and give you better performance. So that's the YJet atomizer, and that design's got to be 70 or 80 years old and still in use. So I know this is a busy schematic, but I wanted to show you how the piping is typically done on a steam or air atomized burner. And it starts at the top left, that line marked FOR. Well, let's start with the supply. The line marked FOS is your fuel oil supply line. It comes down to each burner, makes a right, and then you'll notice there's a 0 to 200 PSI gauge there. And then you go through either a strainer or a filter. You're gonna have a high oil pressure switch, a low oil pressure switch, and then a fuel flow control valve that's controlled by the combustion control that modulates the fuel control valve from high fire to low fire. Then you're going to have 2 safety shutoff valves with proof of closure switches, and then go right to the burner. The atomizing steam typically, this one has steam on the right-hand side. That's that line marked HPS. It comes down, there's a trap at the bottom of that T, and then it goes through a flex hose, and then a low pressure cutout switch. This one shows a differential pressure control valve where you sort of sense oil pressure and adjust your steam pressure to match your oil pressure. Then you go through an automatic shutoff valve and then up to the burner. And you'll notice they don't mix until you get right to the burner. This one has plant air on the left-hand side to the left and parallel to the steam. So I think this was a VA hospital project, and it looks like it's set up for atomizing air or atomizing steam. Now, another thing that genset people that are doing a fuel system for boilers will often do is they'll see the schematic and then they'll call me asking, where do I get this filter? And where do I get these switches? And what kind of valves are these? What are these safety shutoff valves? Well, everything inside this box is going to be provided by the burner manufacturer. And the fuel supply company doesn't have any responsibility inside this box, 9 times out of 10. You may have a PRV at each oil burner, but that may be supplied by the burner as well. So I would say if you're bidding a fuel system for a boiler job, if the drawings don't include this handy little box, I would say don't supply anything upstream of the individual burner PRVs or the individual burner upstream gauges. A lot of times there'll be a lubricated plug cock there too, and that's the start of the burner fuel train. And if you're not sure, see if you can get a submittal or find information on the burner that's called out for the boiler, and that'll tell you where their responsibility is going to start and yours is going to end. Okay. Okay, the first slide, this is how to correctly calculate boiler heat input and oil flow for boilers. your heat input in BTUs per hour is going to be equal to the enthalpy of your steam at whatever operating pressure the boiler is going to operate at, minus the enthalpy of the feed water at whatever temperature the feed water is going to come to the boiler, typically 212 to 218, multiplied by the pounds per hour of steam, divided by the boiler efficiency. So that gets you the heat input in BTUs per hour. These are the equations you're going to use for a water tube boiler because they're typically expressed in pounds per hour of steam. Fire tubes are typically expressed in boiler horsepower, so the conversion from pound per hour to boiler horsepower is 34.5 down there in the bottom. So that's the correct way to do it. The quick way to do it is heat input for a fire tube is boiler horsepower times 33,475 divided by boiler efficiency. Boiler efficiency on oil is going to be around 80%. Depends on the type of boiler. If it's a 2-pass boiler or a water tube, it might be a little less than 80%. If it's a 4-pass fire tube, it might be a little more than 80%. Call it 82%. It's really splitting hairs because when we do the transfer pumps, we're going to put a large safety factor on the transfer pumps. So if you use 80% for your efficiency, you're going to be fine. Heat input for water tubes is going to be boiler horsepower times 12,500, and that'll get you in the ballpark. And again, oil flow in gallons per hour is heat input in BTUs per hour divided by BTU content of oil, usually 142,000 BTUs per gallon. So you might want to take a screenshot of both of these. So, and I'll go back to the correct way to do it too, if you want to screenshot that. Okay, so now we're ready to design the transfer piping for mechanical, we're going to start with air atomization or steam atomization. And it's very simple. And if you've seen how we do multiple day tanks on a genset job, it's very, very similar. We're going to come out of the tank. We're going to go through our transfer pump set, and then we're going to have a supply header, and 90% of the time, we're going to put all of our boilers in parallel. And then we're going to go to a back pressure regulating valve, and that back pressure regulating valve is what is going to control the pressure in that supply header, because back pressure regulating valves they're the opposite of PRVs. A PRV modulates to regulate downstream pressure. A back pressure regulating valve modulates to maintain upstream pressure. And it does this by opening and closing and dumping oil into the return line back to the main tank. And there's really two types of burners. The oil line can deadhead like this one. And if we went back a couple of slides to that VA hospital schematic I showed you, the oil line's there deadheaded at the burner. Some burners are going to have a 3-way valve as their first safety shutoff valve, so that when the burner is not running, they're returning oil back to the return header. So again, you need to take a look at the type of burner that's being supplied and see if it has a return line or not. The advantage to the ones that have return lines is that it allows you to move fuel and move fuel through your strainers before you light off. And that's a pretty big deal. With mechanical atomization, you have some pretty small orifices, but with air atomization or steam atomization, one of the things they taught me when I was doing burner engineering is don't reduce your hole size below a certain point, because if the holes get too small, they're more easily plugged. So we always like to move some oil through the system before we light off the first burner. And whether there's a return line on the burner or not, even if it's plumbed just like this, we can still go turn on the, put a pump into hand and turn on a pump and just get oil moving through the system. And there's strainers or filters in the pump set that'll catch any chunks that are moving through the oil and keep those chunks from getting to the burners where they can potentially clog up an oil gun. So that was it for steam or air atomization. Now we're going to move on to mechanical atomization, or sometimes it's called pressure atomization. Of all the atomization styles, it produces the largest droplet size. So in terms of atomization, it's really the worst in terms of droplet size. However, there's no steam or air required, and this is the number one reason that mechanical atomization is used, because there's no parasitic steam loss and you don't have to run an air compressor, and that's a big advantage. Some of the European manufacturers very cleverly put a clutch between the FD fan motor shaft and the oil pump and engage that clutch when the burner selected oil. So you're using the FD fan motor to turn the oil pump and not have to have a separate oil pump motor. So that's very cool. Mechanical atomization requires a ton of pressure, typically 300 PSI, and that's why you need to have a high pressure pump right at the burner. Turn down for mechanical atomization used to be like 4-to-1, but it seems like some of the burner manufacturers and the European burner manufacturers have gotten better at this, and now can get about 6-to-1. And like I said, it's standard for most European burners, and to take 300 PSI across the oil tip, or most of that 300 PSI across the oil tip, requires very small orifices, and those orifices are prone to plugging. So you need good filtration at the burner. And we can help you with that. We supply filters as well as strainers that can be installed just upstream of these. And I've seen, I saw a European burner one time that had gotten so much crud going through the line that it actually blew out the basket in the Y strainer and the oil line going to the burner, and then all that junk got dumped into the burner, and the entire oil gun had to be taken apart and cleaned to get all that junk out before it could be fired again. So put a good filter or a good small mesh strainer at each of the mechanically atomized burners. So this is what a typical, this is a Weishaupt burner, and it seems like they make a very good burner. And it seems like the other European manufacturers try to copy Weishaupt, even down to the color. So most of the European burners you're gonna see are painted red to look like Weishaupt. And there at the bottom right, you'll see that that oil pump that I was referring to. And this is what we always want to look for when we're doing a boiler fueling job, is look for that pump on the burner, because if there's a pump right there at the burner, then it's going to be mechanical atomization, and our pressure to the burner is usually going to be no more than 10 PSI, and the flow is going to be whatever that pump flows. So here's a diagram right out of the Weishaupt manual, and the pump is there on the top left. That's item number 6. This one shows a bunch of solenoid valves. We go through the normal oil train, and then item number 5 is the actual oil gun, and then there's a return line, and item number 7 is the oil regulator, which in the US we would call the oil flow control valve. And this is a technology that when I worked in the utility industry, we would call this wide range mechanical atomization. And your flow control valve is in the return line. And it's important to note that to get more oil out of that oil gun, as you go to high fire, you close off the oil flow control valve, this item number 7. And that forces more oil into the gun. And then the oil that doesn't go into the gun goes down into that that oil return line. That's that bottom arrow. So how to calculate oil flow on a pressure atomized burner? It's not fundamental the way it is with air and steam atomization. So the first thing you have to do is determine the make and model number of the burners. Hopefully, you know, if you're bidding new construction, hopefully it's on the schedule for the boilers and the burners. And we don't really care what the make and model number is of the boiler. We're looking for the make and model number of the burners. Once you get that, find the burner manual. All all the European burner manufacturers have their manuals online in English units. It usually doesn't take me very long to find the burner manual. Dig through the burner manual. Some are better than others. Most will tell you what the flow of that pump is. Some will not tell you the pressure limitations on that pump. The burner manuals will tell you the model number of the pump. And almost all of the European burner manufacturers use Suntech pumps. So you can look up Suntech and that model number and usually find a manual for the pump. And the pump manual will have the information we're looking for. So here is a snip out of a Weishaupt manual, and it seems like the WM series is what they use most often in the United States. And if you go down to the third line from the bottom, it's got the pump fitted max flow rate modeled in gallons per hour and liters per hour. J6, J6, J7 is the Suntech pump number, and they include the max flow rate. This is the max flow rate that we need to use to size the transfer pumps. And if we've got 3 burners connected in parallel, we're going to take this and multiply by 3. If they say they're only going to run 2 burners at high fire, so only size the transfer pumps for 2 burners, I would resist that, because in most places in the United States, oil is a backup fuel. So they're only going to be burning oil if there's an emergency. And if they're in some kind of an emergency, more often than not, it seems like they're going to be needing a lot of steam out of the boilers, and they might need that third burner to go to 100%. And the difference between the next step up transfer pump set is usually not a lot of money, and the pumps are small, so it's not a lot of pump either. You might go from a 1.5 horsepower pump to a 2 horsepower pump. Big whoop. And the difference in dollars is not that much either. So in this case, the burner manual tells us the type of pump, and it tells us what the max flow rate is. It doesn't tell us the pressure limitations of the pump. For that, you need to go to the Suntech manual. These are snips from the Suntech manual for a J4 and a J6 pump. And it shows a delivery pressure of up to 300 PSI. And then inlet and return pressures are no more than 10 PSI max. And check out that note. NFPA limits pressure to 3 PSI max. So Suntech doesn't understand the boiler market either. Suction height, they're all piped with what they call a 2-pipe design. So the Suntech pumps are capable of 13.5 inches of max vacuum. They're really designed so that they can pull directly out of a nearby tank if they need to. Although we very rarely see that. Usually we're going to have a main tank, transfer pumps, and then a header supplying all the burners. That's what's most common in the United States. Occasionally, in fact, I just saw one yesterday. I saw a boiler design that had a day tank next to each boiler, and transfer pumps pumping from a main tank to all those day tanks. And there's really no reason for that. It adds a lot of money to the project, and nobody wants to have oil stored inside their building if they can help it. And why would you take the risk of potentially overfilling a day tank when you don't have to have that day tank? You're much better off doing a low pressure loop. If it's a mechanical atomized job, you're much better doing a boiler loop, a low pressure boiler loop, than you are using day tanks. There's absolutely no reason to use day tanks on a boiler job. Although as soon as I said that, I realized we just helped design a job in Chicago where it was like 400 feet between the main tanks and the boiler room. And we did put a day tank in the boiler room with transfer pumps to power the boiler loop, and transfer pumps to get the main fuel from the main tank to the day tank. But we did that because there was a huge distance between the main tank and the boiler room. That's the only exception I can think of. Otherwise, do not use the day tanks with boilers. This was not in a Weishaupt manual. I believe this was in a Riello manual. Riello is made in Italy and they They make a burner very similar to Weishaupt. And I included this diagram because it shows you how these burners with onboard pumps, they're not specifically designed to have a tank nearby, but this one shows you the pressure and the limitations. And unfortunately, this is all I snipped. I didn't save this manual, so I don't remember what H and V are, but it worked out to about 10 psi positive pressure and no more than about 13 inches of negative pressure. But again, check the manual on the pump, because that's going to tell you how much the pump is going to flow, and also the pressure and vacuum limitations of that pump. The piping's a little more complicated than what we showed you before, because we're going to have return lines. And this animation isn't perfect, but we show the oil coming out of the main tank through the pump set, up into the supply header, to the oil pumps on each burner. And then the oil pumps have a return line. We're going to header all those return lines together, and we're going to dump that fuel back into the fuel oil return header. And we're going to size our transfer pumps for the flow of these 3 burner pumps, and we're going to set the back pressure regulator at no more than what those pumps can handle. In the example I just showed you, that's 10 psi. So Preferred offers 2 different types of pump set packages. We have an SATPS. This is a semi-automatic transfer pump set that's intended for manual operation. It has very minimal relay-based controls. About the only real control function it does is it will automatically switch over lead pumps each time there's a call for operation. You get a handoff auto selector switch for each of the pumps. You get a motor starter for each pump. And there's no digital communications at all. It's all old-fashioned relay type controls. I would supply these for water tube projects where we know we're going to be energizing pumps by hand before we try and light off a boiler. There is a terminal in here that accepts 120 volts from the burner flame safeguard systems that'll bring on a pump automatically if you want to. So if you're going to do manual light off or automatic burner light off, we can automate it with this type of pump set. And this is the least expensive of our 2 types of pump sets. The other one that we supply, and this will be more familiar to the Genset fuel people, is our automatic transfer pump set. This has a little PLC in it and a 4-inch color touchscreen. And with those PLC controls, we can do anything you want in there. So if the plant wants to automate their transfer pumps to come on whenever a burner is selected to oil, we can do that. We can bring in the call for fuel individually from each boiler, so that at the transfer pump set, you can see which boiler is calling for fuel. This has automatic failover lead lag logic, where we'll always supply a flow switch that gets installed in the discharge of these pumps. And if a pump is commanded to come on, that flow switch has got to open within a time delay limit. Otherwise, we're going to sound the alarm and start the other pump. It's the same lead lag logic that we use on our gensets. And it's a little bit of an automatic lead lag. So in case something fails with one pump, it'll automatically switch over to the other pump. And if neither pump proves flow, then we're going to go into alarm and we're going to de-energize both pumps so that we don't burn up the pumps. And the number one reason why the flow switch won't prove is that somebody has closed a hand valve and wasn't aware. So, hopefully the boiler technicians will line up all their valves before they try and fire on oil, but sometimes they forget a valve and miss a hand valve. It happens to the best of us. You still get a handoff auto selector switch for each pump. And because we've got a little PLC in here and a 4-inch color touchscreen, we have Modbus, Ethernet, and BACnet communications in case the plant wants to know what's going on with their pump set. We can also throw a tank gauge into this so that we do the level sensing and leak detection in the main tank. If you've got containment piping, the leak detectors can be wired into this PLC or into the tank gauge. So even though it's not strictly required, more often than not, we end up providing this style of pump set even for boiler jobs because of the processor and the color touchscreen. The last piece of equipment I wanted to show you was the back pressure regulating valve. This goes at the end of your supply header, and the discharge of this valve is the beginning of your fuel oil return header. We make 4 different sizes. The difference really is in capacity and spring range. So for fire tube boilers or water tubes, you're usually going to be the 12765. That's a 30 to 150 psi spring. For a mechanically atomized, it's usually the 12763 with a 5 to 20 psi spring. And we showed you how to pipe these. And then here's a common complication. When you're dealing with new boilers or a boiler replacement project, there's going to be boilers specified. There's going to be boilers and burners on the schedule maybe, and you're going to design the transfer piping and select the pumps and select the back pressure regulating valve. And then there's a chance that the specified or scheduled burners are not going to be what ends up getting supplied on the job. So after the boilers are awarded, the plumbing engineer needs to go back and get the submittal on the boilers and the burners and make sure that if you designed around steam or air atomization, that pressure atomized burners didn't sneak in. Because if it's going to be pressure atomized burners, then your oil pumps are probably going to need to get bigger, and your back pressure regulating valve is going to need to change to one with a lower spring range. And that's happened to me many times, where in fact it's happened before where we didn't catch it until our pump set's out in the field and we find out that there's an onboard pump on the burner, and we need more flow out of the pumps. Like I said before, I size transfer pumps pretty generously. So sometimes we just ate into our safety factor. And then sometime, I remember one occasion where they said, we're never going to run all the boilers at high fire anyway. So these pumps are fine. But on new construction, make sure that you get the burner make and model number after the boilers are awarded to make sure that it's the same type of atomization or the same type of burner that you designed the transfer pumps for, so that you can fix it on paper before it gets out to the field. That's virtually everything I know about transfer pump sizing for boilers. If you have any questions, we're going to do this is going to go on YouTube first, and then we're going to run this webinar live in a month or two, and then we'll do Q&A after that. So stay tuned to Preferred's webinar schedule for when we do this one live. Okay, and thanks everybody for attending.